Hi everyone, and thanks for joining us for the contributed talks for the Maple in Education session today. We have a number of talks lined up for the hour highlighting Maple's impact on education. Each presenter will provide a summary of their work, and then afterwards, we will invite questions from the audience. When we reach time for questions, I'll invite you to either unmute and ask a question or type your question in the chat at the bottom of the screen. So in the interest of time, we're going to go ahead and get started. I'd like to introduce our first speaker, John Pais. So John, if you'd like to share your screen, you can go ahead and get started.
Greetings. In this talk, I will describe a student assignment, which is a computational exploration focusing on commutators. In computer science, this might be known as a nifty assignment. The goal of this assignment is to enhance student understanding of solvable and non-solvable groups using visualization and computation. The first part of this exploration is for the students to implement the commutator definitions of some standard concepts. And let's take a look at those. I have to apologize. I'm only going to be able to go over these very briefly. You can probably look at this again when the video is posted. So there's a standard definition of a commutator of two elements of a group. It's going to be equal to the identity if and only if the two elements commute. Here's a commutator of two subgroups, and then the commutator of, if you take commutator of G with itself, that's G prime. Okay, that's the commutator subgroup, and a group is perfect if G is equal to G prime. The nilpotency sequence is pretty standard, defined with commutators, and basically if this sequence ends on the trivial subgroup, then the group is considered to be nilpotent. Similarly, the solvability sequence is defined standardly here with commutators, and if it ends on the trivial subgroup, then the group is considered to be solvable. This is also called the derived series. I apologize for going through this really quickly, but I won't try to give you a good overview. So then you can use what are called left angle based commutators, which is to basically take H and then stack as many commutators to the right of K as you possibly can. You've reached the trivial subgroup, then you can say that K angles H. And if you take all the elements of K and G that angle H for all H and G, then that's the definition of the fitting subgroup. And it turns out the fitting subgroup is the largest normal nilpotent subgroup of G, and that's Bayes' theorem. Of course, I'm doing this backwards. So I'm defining this in terms of the commutators and then citing Bayes' theorem. In addition, for normality, we have a test here using commutators. And furthermore, for the normal closure of a group, we can define that using commutators, and we can also define the descending normal closure using commutators. This means that, essentially, since descending normal closure is the same as subnormal closure, this means we have three different ways to define the subnormal closure. It turns out that this is the standard way to do everything in terms of conjugates. So what I'm contrasting here is doing it with commutators and doing it with conjugates. Okay, so then the students would test their code that they wrote on, of course, I would anonymize these groups. I wouldn't tell them what they were when I give them to them, but here's what they look like a little bit. So in this case, these are 4x4 matrices of complex numbers, and those are the group elements. And let me quickly scroll down here and show you the expected output that I would want. So for this group, GL2F5, and the expected output would be, okay, so I would compute the nilpotency sequence, the solvability sequence, and the fitting subgroup. It turns out that this group is neither nilpotent nor solvable because it ends at SL2F5. And however, its fitting subgroup does count for something. It's C4, it's very small. I did the same thing. This is like examples of what I would expect from the kids. I did the same thing with the maximal subgroups. And so you can see that with the maximal subgroups, this is not nilpotent, but it is solvable. And the fitting subgroup in a solvable group turns out to be a little bit bigger. It's C20. And similarly over here, this group is not, this maximal subgroup is not nilpotent, but it is solvable. And its fitting subgroup is C24. So those are both abelian groups. Now, if you look at U2F3, we have a kind of similar situation. You know, it's not nilpotent, but it is solvable. In this case, we get a fitting subgroup that's a P group, which is C4 circle D4, which is a non-abelian P group, the poly group. Okay, that gives you a quick idea of how I would expect the kids to, implement the stuff and test it. And let me just say one more thing about that, and that's testing the descending normal closure. So what I did was I defined it both in terms of using conjugates, which is the first way, and the second way in terms of commutators. And I basically computed the descending normal closure of C2 for, using both methods, and I got the same thing. And I did it with a bunch of conjugate subgroups and got the same thing. That's what I expect from the kids. Okay, let's go back and continue looking at the exploration and the other portions of the exploration. So that's the first part of the solvability part of this exploration. And then there are these, what they would do next was with the code they have and creating new code, they would verify these, interesting and useful theorems. And it turns out I won't have enough time to go through all of them. This is the standard valent, join theorem for a finite group. It's not true for infinite groups. So that, that's a kind of interesting example. And this theorem shows that in addition to, the join being subnormal, by the way, that's my symbol for subnormal. In addition to the join being subnormal, we'd have the relative closure of K with respect to H is subnormal, and the commutator is subnormal. So there's the commutator entering it. Let me just say one thing about this Stone-Hewer theorem. This is a very deep theorem for all groups. And it says essentially that the join of finitely many solvable subnormal subgroups is solvable. And this is a version of it with just a pair of subgroups. And basically what it does is it takes the join and it creates a function that basically is bounded by the product of the two subgroups. They're using their solvability sequences. In this final theorem here, it turns out that the commutator version of the descending normal closure is necessary for the proof of this. So that's tipping my hat to all the commutator stuff that I was talking about. So that's the end of the solvability part. Now this is the non-solvability part. The non-solvability part is okay, as we saw in the abstract, we know that if we have a non-abelian simple group, then it's not solvable. So the question is, okay, can we replace simple with some other property that's not so strong? And so then I give them some properties to consider. Basically, the group is perfect, monolithic, G mod Z of G is simple, the fitting subgroup is trivial, and then if 1 and 3 are true, then the group is quasi-simple, and then some other ones. Then I give them some references to work with, and let me just put those on the screen for a second so you can see them. Okay, for a second. And then I have like a detailed worksheet that I filled in answering some of those questions. And of course, I would give them this as a blank worksheet. Let me just scroll through that whole thing. And then also I would give them examples. Oh, sorry, that's not what I wanted to do. Let me back up. Okay. And then I've given them some example subgroups and then fill in the chart with respect to all these properties. And of course, I would give them this as a blank document too, so they could fill it in. Okay, finally, there's a project in which they would try to compute the Schur multiplier using the Hop formula and also in terms of the kernel of the central extension of G. It turns out that computing the Schur multiplier using the Hop formula is, according to Gordon, is an undecidable problem. It's undecidable in the sense that it's whether or not it reaches the trivial subgroup is undecidable. Okay, now let me jump over to, I wanted to hit the AI queries part. So let me go to that. Okay, so my experience, and I use basically the standard version of Grok that you just pay a little bit extra for when you get an X account. And it does okay with standard definitions and standard proofs that are on the web. It has those, it can reproduce those. However, it's not so great with more complicated things. So for example, if you look at, if you look at property 3 that I had up there, namely that G mod Z of G is simple, what I did was I asked it, hey, can you tell me if there's a special name for G mod Z of G being simple? So it did a bunch of stuff, a bunch of palaver talking, et cetera. Then it gave me an example. An example it gave me was an example in which it claimed that A4 was simple in 2 places. So that's clearly wrong. And then another thing it did that's clearly wrong, this was a tailspin into obvious repeated guesstimation errors. I asked it to order a bunch of double covers of sporadic groups, order them by their group order. Okay, and it turns out this is about the fifth time I asked them to do this, and it can't do it. Okay, it will explain and tell you how wonderful it is, and oh, now I have the final corrected list, but it can't do it. Now the tough one and the most concerning one is this. I wanted to see if it could interpret a mathematical logical statement in ordinary language and what it would do with that. So the statement is constant. The gist of it is the following: given a property P, find the minimal subset of the other three properties that implies P. Okay, so for example, P1. If any, it may not be any. Okay, so when I asked it to do that, there was a whole bunch of palaver. And in here, it said that P4 was the minimal subset that applied P1, and that P1 is the minimal subset that applied P4. And it turns out that's not true. And so I asked it to write a clear, detailed proof that properties P1 and P4 were logically equivalent. And it claimed to do that. I excluded that, and it came to that, final conclusion again. So this is pretty bad. This is also a tailspin into an incorrect logical proof. And the reason being that SL2F5 is an example. SL2F5 is the binary icosahedral group, which is order 120, and it's perfect, but its fitting subgroup is C2. So it doesn't satisfy the Stephan property. So it doesn't have a trivial fitting subgroup. For the other direction, S5, the symmetric group on 5 objects, it's a group of order 120. It has a trivial fitting subgroup, but its commutator subgroup is A5, right? So it's not perfect because it's not equal to, G is not equal to its commutator subgroup. Okay, so I guess what I would say here is that for me, I guess I'm partial to abelian AI, and that's when AI equals IA, namely when IA stands for information accessibility. But intelligence, not so much. Okay, I think I'll end it there in case there are any questions. I really burned through that. Sorry for going so fast and talking so fast.
All right, thank you, John. That was great. So now if you have a question, please unmute yourself and ask, or you can type it into the chat.
Well, let me just comment then, if there's no questions, let me just comment that my takeaway here is, in observation 2 is, Grok may be able to correct itself or not. It is committed to a solution path generated in the context of your query, and so it may exhibit extreme tunnel vision and or get lost in a tailspin of contradiction and or guesstimation. Also, when called out, and I called it out, right, and had a dialogue with it, an ELIZA-type dialogue, Grok will apologize, admit it's false, and reflect specific criticism with ELIZA-type responses while making excuses that it wasn't designed to be an exact database or a precise calculator or a rigorous prover. And my main bone to pick with this is it should be saying this up front. So the fact that students might be pulled into this and think they're getting things that are correct and then find out they're totally wrong, that's a problem. Okay,
And
thank
it
you.
looked like we have a couple questions in the chat. So did you use Maple to generate those graphs of group relations is one of the questions.
The examples the graphs? No,
Yeah.
that's I could, but I didn't, right? Let me show you the references again. I used Tim Duckacher's group names website. Fabulous website. It has, it has the lattice of subgroups for many, many groups up to around 450 or 500 order. And it's very, very useful in kind of interactive feedback when you're trying to explore. Let's say I give you, a set of group elements in terms of matrices, and I want you to tell me what it is. And so it's extremely helpful doing that. You could just mine it, find subgroups, and then try to interactively go back and forth with Tim Duckacher's group names and look at the groups of the corresponding orders, and it's actually pretty fun to do that.
And one final question from the chat. So long as AI is based on probabilistic reasoning, will it ever get math right?
That's a great question, and let me go back to what I skimmed over really quickly. You may know that Richard Sutton was a Turing Award winner in 2024. And this is a quote from him. As Alan Turing has said, intelligence is the ability to learn, change from experience, but LLMs can't do that, right? So basically, I think it can't. Basically, once you've done your run, then it's doing it. It's creating its response with respect to, all the training, with respect to, its statistical pattern matching, whatever it did, but that's an artifact that it's now referencing your whole query to. So you can't get out of that. It can't change its mind. Like, for example, with the contradiction I found, if I was a human mathematician, which I think I am, or a student, what would I do? I'd go back and look at what was going on there, and I'd try to like reprove it. I could like change my mind and try to, find a way in which my proof failed and or find a better proof if there is one. I hope that makes some
Awesome.
sense.
Yes, so we got a comment and it'll be a great way to end the talk. It's really cool to see the pitfalls of AI in higher level math like this. So thanks, John, for sharing your talk.
My pleasure. Thank you for listening.
Hello, everyone. My name is Juan Ramirez, and it is an honor to be here at the Maple Conference 2025. Today, I present Educational Digital Twin for Microchip design in Panama using Maple and MapleSim. This dream is a key piece in the effort to prepare the next generation of engineers in my country, Panama, and support the national semiconductor strategy. To introduce this dream, I want to highlight the central objective. Our project aims to support Panama's national semiconductor strategy by developing an educational digital twin focused on microchip design and simulation, utilizing the powerful tools of Maple and MapleSim. It is an innovative response to current educational challenges in my country. The strategy, as articulated by Dr. Eduardo Ortega, General Secretary of Science and Technology of Panama, focuses on three critical areas of opportunity. The supply and logistics chain, semiconductor design, and assembly, testing, and packaging ATP. Specifically, the national aspiration is concentrated on engaging in the initial design and final ATP manufacturing phases. To realize this goal and ensure product quality, a core requirement involves developing specialized cleanroom infrastructure. The Senacid, in collaboration with the Technological University of Panama, UTP, is currently establishing a small-scale cleanroom facility dedicated to student training in equipment usage and quality control for semiconductors, which aligns with broader efforts to cultivate the necessary technical talent for the engineering and technology sector. The context shows us a great ambition for Panama to become a regional hub for semiconductor development. However, STEM education fields face significant challenges such as school closures, strikes, and crucially low accessibility to specialized microelectronics laboratories. This is where Maple tools offer a potent solution, serving as a digital platform to bridge complex theory with engineering practice. Allow me to share my background. I have been a STEM YouTuber since 2017 and was named a Maple Ambassador in 2025. Through my channel, I have produced over 335 educational videos. As a self-learner, I have advanced significantly in microelectronics design using precisely Maple and MapleSim. In my personal experience validates the power of these tools for advanced self-learning. My YouTube channel, which has an audience of students across Panama and Latin America, has focused on physics topics and has over 1,000 subscribers. It is my platform for disseminating knowledge, and it is now the main vehicle for integrating Maple tools into engineering didactics, taking the learning of basic science to a more accessible and visual level. We are currently in the intensive learning phase of Maple and MapleSim. The next phase is the most exciting, building the functional educational digital twin for teaching microchip design. To ensure relevance and impact, we already have institutional visits planned with key stakeholders in Panama, such as IEEE Panama chapters, Senacid, UTP, ITSE, and private partners. Now let me show a little sample of my videos. First, we will watch this. This is a video about diode. And I use STEM techniques like animations in PowerPoint. For example, this. You can see a view of the diode, internal structure, anode, cathode. And I'm looking for the best explaining of the draft current and later I will use, in this case, Maple for a problem explanation. I write the variables and I explain the problem and solve it. In the next video, I use MapleSim, in this case, for the simulation of a circuit, a very basic circuit with one diode connected parallel with a source, in this case a direct voltage source, and I run the simulation. In this case is the same problem as I solved with Maple, and I compare the results with the results obtained with Maple. Let me talk about the impact and vision of this dream. The future vision and impact are immense. We seek to provide direct support to national education and research in microelectronics. We want to foster student motivation with cutting-edge STEM tools and, above all, create scalable teaching models based on the MapleSim digital twin. This is key to democratizing microchip design education. I have currently managed to simulate diode behaviors using MapleSim, as you can see in one of my videos. In conclusion, this dream is an innovative and strategic solution for Panama and other Latin American countries. By using the Maple and MapleSim digital twin, we overcome current educational challenges, accelerating the development of Panamanian talent in semiconductor design and ATP. Our vision is clear: to train the next generation of professionals and in doing so position Panama as a regional hub in the microchip industry. Let me show to you the end of each one of my videos. Thank you very much. And now I hear your questions.
All right. So in the meantime, I'm curious, Juan, about the current status of this long-term project. Like, what steps do you plan to take to move this from the learning phase to the building phase of the functional digital twin?
Well, thank you, Aaron. Panama is currently in the learning phase of its national semiconductor strategy, with the framework defined. To urgently transition into the building phase, I will undertake the necessary steps to meet with Engineer Dario Solis, National Commissioner for the Microelectronics and Semiconductor Industry, and with Dr. Eduardo Ortega from National Secretary of Science and Technology. The main goal of this meeting is to integrate Panamanian engineers and designers by establishing a digital twin platform. This platform is proposed as a vital virtual laboratory for advanced training, design creation, and generating deep localized knowledge, complemented by my background as an industrial engineer, STEM YouTuber, and Maple ambassador. To facilitate this immediate transition, two specific steps are proposed. First, organize the inventory of Panamanian talent to strengthen the ecosystem for the digital twin, providing a functional, immediate, cloud-based ADA, electronic design automation, environment for design simulation. Second is to establish the integration of the digital twin project with current ongoing projects in favor of the national semiconductor strategy, ensuring the digital twin complements and enhances existing initiatives, serving as a validation and development platform that accelerates the country's knowledge and productive capacity in the microchip sector.
Okay, so first of all, I want to extend my greetings to all you listening from South Texas. Texas A&M University in Kingsville is part of the Texas A&M system, of which there's 11 or so like universities in that system. So today what we want to do is discuss the topic shown here. And what this really is all about, it's about a core subject, which is part of our curriculum in our graduate degree programs. And actually, transport phenomena is a topic that's actually a core subject in, I would say, nearly all of the graduate curriculums in chemical engineering. So one of the key questions, and I call it an ongoing challenge here, is how can we use Maple to basically transform how we teach students to basically develop what I call a deep knowledge of transport phenomena. And probably more importantly is as they develop that knowledge, it's really a fundamental underpinning of all various aspects within chemical engineering, and actually spills over into other areas of science and technology. And we want to try to do this in a way that they have this knowledge embedded, so they can then use it as they go forward and they perform their, say, research for their master's or their doctoral degrees, or they go out into industry or say research, and they work on emerging type of technology problems. Now, one of the questions that comes up here is, why is this subject important? Well, if you look at the discipline of chemical engineering, one of the key things, first of all, it typically involves a molecular transformation. That is, we're taking some kind of molecule or molecules and we're converting those into like products. And those processes always occur in typical various multiphysics. And those multiphysics can occur over a significant range of time and length scales. Now, over here on this side of the slide, you can see some examples. For example, say we want to determine the temperature profiles in a like lithium battery pack, or we want to maybe like design some type of specialty chemical plant, and we're going to do that in a way that basically optimizes the like production. And so you can see here, these are just some profiles from actually from a more advanced type of simulation. Say you want to understand better what happens in like a real stir tank type of system used to perform various types of like reactions. Another example down here might be this what we call a rotating packed bed type of reactor, which is used not only to perform chemical reactions, but also started out being a new way to do like distillation that was developed at ICI. Another important process, an example of like multi-phase flows, is the production of polycrystalline silicon, and that's done in a like a fluid bed reactor. And there's a number of phenomena which occur in that case: heterogeneous type of like nucleation, homogeneous type of nucleation, gas solid contacting, and just a whole assortment of like phenomena. So basically, this subject really provides, as indicated on number 2, it's really a fundamental framework for creating not only mathematical models, but the reason why we're doing that is we're trying to develop a rational approach for analyzing what's happening on a particular scale, but also for scaling, and so that scaling is going to be successful. So this is really, as I mentioned in my opening comments, that it's a core subject and it's a critical skill requirement in chemical engineering type of education. So when we talk about multi-scale, physics types of systems, here's a view from a chemical engineering type in a chemical engineering type of system. So what we're doing is we're taking chemistry, which is occurring on the atomic and like molecular scale. Maybe that's occurring on the nanosecond, femtosecond. It just depends what it is. But we're looking at a very fast time scale and with molecules that interact on surfaces. We're trying to describe how those chemical reactions occur on say, solid type of catalysts that are undergoing different types of processes, which are illustrated here. Say, absorption of the reactants, basically, and undergoing different types of elementary steps and described by different types of like rate constants. Then we want to then take that chemistry and try to put it in a practical type of catalyst particle, maybe, and shown here, and that particle may consist of maybe metals deposit on a solid, and then eventually they will go into some type of reactor, and that reactor could be very large. That device could contain 10 to 15,000 25 millimeter tubes that are 10 to 20 millimeters in length. And so in that we have a multitude of multiphysics which are occurring. So understanding the subject is very important to be able to do that. Okay, how do we get into doing this? Well, we first introduced it in our graduate courses about 15 or so years ago, which was shown there in the mathematical methods course, in this course, and the reaction engineering course. And we referred to a nice book written by White and Subgroup as a reference. And the approach that I used, we just used it learning by example. Started out with like simpler problems, and then we worked our way through it. And what we did first, though, we solved those problems using like manual methods. And so what we did then, once the solution was developed by a manual method, and students basically saw the labor involved. We said, well, let's look at another way of doing this, and that's where we introduced Maple. And we've provided some a real motivation by offering extra credits and other means. And actually also assigned like a course project where they could do more in-depth type of analysis. Now, the fundamental underpinning of transport is basically the equations shown here in like vector form, which involve, I call it mathematical physics, for conservation of like total mass, conservation of like momentum, angular momentum, conservation of energy in the presence of like mixtures, and also conservation of like species. And these are all really the subject of a landmark book that was first edition written in 1960 by Bird Stewart and Lightfoot. So Maple, with its tensor calculus pack, is a very useful tool for students to understand how do we transform these tensor vector form of the governing conservation principles, and we apply those to problems. Now, what I'm not showing here is also the macroscopic equations, which are obtained via integration of these, which we also study in that class. All right, so when we do that, we end up with the equation of like continuity in the different coordinate systems. But in Maple, and we actually can derive those using like a shell balance approach, and we could extend that to other coordinate systems because many problems can be posed in a coordinate system other than the ones that we see here. So the vector calculus package is very useful for that. And of course, the equations of motion, here's an example of what they look like, the full-blown 3D ones for the case of constant density and viscosity. So what we do when we solve a problem is we basically make some assumption about what the velocity field and pressure field depends on, and we then eliminate the terms and we end up with a reduced model that we must solve. So here's the Navier-Stokes equations in the cylindrical and spherical coordinate system. And so when we first look at that, it looks very complicated, but when we start eliminating terms, then we can end up with a reduced model. So here's a summary of some of the problems that we solved. There's many. Here's one Stokes flow, what it means, low Reynolds number flow between concentric spheres, which you end up with equations which look like shown over here. Radial flow between parallel plates. This is kind of a problem in like lubrication. So we have a fluid enters and it flows out radially in the plates. And the problem then is to find the velocity field. Once you find the velocity field, to basically integrate that over the cross section and to derive an equation for the mass flow rate. Another interesting problem occurs here, and this is really has origins in measuring basically the viscosity of fluids using what's called a Couette type of say viscometer. So the fluid is placed in an instrument that looks like this, and we basically measure the torque that occurs when this spins, and from the torque we then can extract the viscosity. So this can be done for both the inner and outer cylinder rotating, and this shows a view of what we can generate from the Maple solutions. Now, those few examples there was no energy equation involved. We could include the energy equation, which is shown here for the case of a pure Newtonian fluid at constant viscosity. And here we see it in the different coordinate systems. And of course, you would recognize that the right-hand side, of course, is the equation of like conduction, and this is transport of energy due to convection. And then we have the viscous dissipation term, which is shown here as mu phi sub v. So an example of this might be this problem shown here, where we have a rotating type of say viscometer, and what we want to do is we want to understand basically what we want to do here is we want to basically be able to predict the temperature profile of the energy that occurs by viscous dissipation, which is caused by velocity gradients. We want to be able to couple that with the like momentum balance. Here's a nice problem in like conduction. We have a sphere, and we look at the shape that occurs when this intersects with a cone. And so for Maple, we could solve that problem and generate a slice of the temperature profile. We also did the same problem using the finite element method, and this basically shows a mesh and a temperature field that was created as an independent type of verification. Another nice problem here is heat transfer from a wall to a falling film. This might be important if you're designing some type of, say, evaporator, where you want to, say, concentrate a like solution. So you want to examine when the fluid flows down the wall of an evaporator tube, how does the temperature profile propagate in that system, and how is it affected by other system parameters? In this case, you're looking at developing a like similarity type of solution to the governing energy equation, which is shown up here. And using Maple, we're able to do that very nicely. So wrapping up here, so what we found is that it's really a very powerful tool for teaching like the subject. Of course, this subject is taught on different levels, kind of entry level. Then we can go into more advanced topics, which are done in a subsequent coursework. The various features in Maple are very powerful and basically allow one to incorporate not only analytical solutions, but also we could, of course, do some, of course, like numerical computing. The graphical part is very useful for getting an insight into what's going on. And what we find is that when students are actually doing this, they really get a lot more like engaged, and we found that they carry that knowledge forward into their other subsequent courses. So with that then, that's the end of my slides. And what I might be able to do here is, I don't know if I would be able to maybe share one of my Maple screens here. Let's see if I have it available here. Okay, let's just go back here to one of the examples here. This is the problem of the like a rotating type of system. So we start out with the starting equations, and then by making the required assumptions, we could then reduce those down to the required form. And so using the basic commands, we could then do that for all the different components of the momentum equation, which are shown over here. And then what we're able then to do, once we get that down, we could identify the constants in the subsequent equation that we solve. And then we then can take that and find the equation of the surface of that, and that comes from the pressure field equation. And then we can then look at the different cases depending on which cylinder is rotating and so forth. All right, so that gives you some idea of the equations involved. And then finally, we can then generate the surface plots, which show how the surface of the fluid behaves as a function of the angular type of velocity. Okay, so with that, in order to keep within my time limits, I went a little over, but thank you, and I'd be glad to entertain any questions or.
All right. In the meantime, I will just ask, which aspect of using Maple in teaching transport phenomena do you find gives students the clearest insight into underlying principles?
Well, I think what I found is that when they first solve some problems using the kind of what I call the manual approach, when you take the like governor equations and then you like reduce those down and you solve it like manually, then when they go into Maple and they do that, then I think they have an idea of what are the operations they have to perform, and it's a matter of them understanding how do you translate those operations that you do manually, how do you translate that into kind of Maple land where you have to really think the way that the software thinks. All right, and I think once they develop that, then they're able to really, these are like weekly type of assignments. They work in usually groups, and we have them come up and of course talk about their solutions. But I think generating the solution, but then taking that and being able to derive some quantity and to make and look at the parametrics, how do the parameters affect it, and to see that, I think graphically, that's a very useful outcome as part of the problem solving. But I also think it gives them insight into the complexity of what happens if they would, want to introduce some other aspect to it. That is, rather than solving the problem in say 1D, to do it in say 2D, and of course eventually do it in like 3D. And those are things that they've done on and more advanced aspects of the class.